So I thought we'd talk a little bit about the audio problem in my Amiga 1200 that I recently acquired. I've got one audio channel that doesn't work. It's quite potentially one of the DC blocking caps is bad. I don't know that. We'll talk about that in detail as we get further in. So I went looking for resources on the internet to help me with kind of coming up with a troubleshooting plan for this. And one of the documents I found is this Amiga A1200R1 schematic from amigawiki.org. Very nice document. Somebody put a lot of love into creating this. I believe it's redrawn, I believe, from the original schematics. I don't know that for sure, but I believe so. It's just a great document. It's pretty easy to follow if you can read a schematic. So what I did here was I went through the document looking for the audio section, and what we see here is the Poly chip output, the right and left channels. There's some amplification and filtering that go on here in this op amp, and eventually the signal feeds out to the audio jacks on the back of the system. So, and we'll talk about that in a little more detail in a minute. The other thing here was this audio power section, which is interesting, and the audio decoupling. So I pulled these three sections out of the schematic. Let me find the picture here. Let's go back and find that. I pulled those three pieces out, pasted them into a PNG file, added a few labels to make things a bit easier for me to follow, and got everything I'm really concerned with on the same page. So let's kind of talk this through. I'm going to start in the audio power section. So U3 here is the Poly chip. I've added the Poly label to it. It's fed from 5 volts through a 1 ohm resistor. There's the VCC input pin on the Poly chip and the ground pin on the Poly chip. And there's this audio ground reference output on pin 37. And what's going on here is we have an audio ground reference. That's the ground symbol with the word audio underneath it. And that ground is separated from the system ground as we see over here. It's just done to reduce noise. So I've got switching power supply noise and system noise and all kind of stuff going on here on these power rails. And what you see here is there's an audio ground reference that's brought out of the Poly chip to this signal. Notice this isn't connected here. There's a ferrite bead that sits between system ground and that audio ground reference to block all of the switching power supply noises and other noise from getting through. So it's blocking essentially RF kind of noise. So it'll make the audio section a little bit quieter. So we have this audio ground reference that gets used in various places in the circuit here. You'll see it here, you'll see it here, you'll see it here, you'll see it here. So although this is ultimately voltage reference to the ground in the system, it's a separate ground that's used to reduce audio noise. The second thing you see in the power supply here is, again, there's VCC and ground, and these feed over to these two resistors here. They're 1.02 k ohms. They're both equal value, and basic Ohm's law tells us that if I have 5 volts across these two resistors, it becomes a voltage divider network. And I should see approximately 2.5 volts here. So it creates this AV reference of 2.5 volts. This has got a couple different filtering capacitors on it, again, to, I believe, deal with noise. There's a small cap and a larger cap. So we need to keep that in mind. There's this reference. Notice that the audio ground reference comes back to the center of these capacitors here. Again, there's a small one and a large one. And again, that's to clean up noise at various frequencies. And this produces the plus audio voltage and the minus audio voltage. And these will be basically minus 12 and plus 12 with some filtering. And then there's this audio ground reference that sits in between them. And again, this becomes isolated from the system ground, again, to reduce noise. So we've got a few things here to look at when we get down into the schematic down below. We get into the actual audio section here. We have the Poly chip here, and we have the right and left channel outputs. And I think I mentioned this up above. This audio ground reference also comes from the Poly chip. So we've got our audio outputs. They come to an LF347 op amp. Notice here that the positive side of both of these op amps goes to this voltage reference. That's this 2.5 volt reference. So my assumption here is that these audio outputs swing from 0 to 5 volts. The Poly chip's powered from 5 volts. and swing someplace in between, that 0 to 5 volts. And by having this 2.5 volt reference here on the positive input, I can get the output of the op amp to swing between plus and minus 12. The op amp is, of course, powered here on pin 11 and 4 from the plus and minus 12 volt rail. So this is essentially taking a 0 to 5 volt signal, at least what I believe to be a 0 to 5 volt signal, and converting it to more of an AC signal centered around this audio ground. So this is really the first stage here. The output then that is now swinging above and below the ground rail is then fed through a little filter network here into a second stage of the op amp that I believe it's really just an amplifier at this point. So it's taking that digital signal, converting it to essentially an analog signal here, amplifying it, and feeding it through to the output. So an interesting note here on these audio output jacks is you'll notice there's 3 pins, 1, 2, and 3. And what happens here is if I plug a speaker into only the right channel jack, because this contact inside of the left channel jack is closed, the left channel audio gets fed up through this bridge line. Am I tracing that correctly? Gets fed up through this audio bridge line. Actually, I'm drawing this wrong. Gets fed up through this audio bridge line to the right channel audio and essentially mixes right and left channels. So you get a mono audio out with only one RCA plug in here or with one RCA plug in here. If you plug both right and left into your amplifier, that bridging contacts are opened up and you get stereo audio out. So this confused me for a long time because I'd plug in one speaker and it would work. I'd plug in the other speaker and it would appear to work. I'd plug both in. And I believe the right channel is the one that cuts out. I don't know for sure. And finally found the schematics and this little bridging circuit and came to understand why. And that really only one audio channel is working. It's being fed to both sides through the little bridge here. And so I appear to get audio out. The other channel isn't working. And with the 2 RCA jacks in, the channel that's not working thus doesn't produce any audio out. So I think we've kind of talked through this. Trying to think if there's anything else here to say. There is this audio filter switching circuit here. And if the audio filter switching circuit is on, these 2 MOSFETs are turned on. Essentially creates a short across the resistors here. And removes the filtering that goes on here to help filter the the signal. So I find this kind of an interesting little circuit. So this filtering can be turned on or off with this digital pin here. Because I've only lost audio on one channel, and this circuit affects both channels, I don't think this is core to my issue. I could have an issue here where one of these MOSFETs is shorted. And what that would do is it would just pass the audio through, and that channel would still work if the audio was there. So if this MOSFET was shorted and this one was working, I should still get audio through and out. Another thing I wanted to mention here is there's a bunch of things this issue could be. It could be cracked or cold solder joints over here on the Poly chip. If the PCB trace, the right channel here, isn't making good electrical contact to the Poly chip, then the audio signal would be lost at this point. We'll just talk through the right channel here and assume that's the bad one. If that audio signal is making it to the PCB trace, and this op amp is bad, well, that would obviously cause us an issue. If the solder joint to this pin was cold and the audio signal was getting up the PCB trace but not into the chip, again, it would block the audio chain. So I'm really kind of following here the audio through the audio chain. Assuming the audio is getting in and the AV ref voltage is correct here, I should get audio out that's swinging above and below the system ground reference. So we can follow the signal on further. If I had a cold solder joint or a bad resistor here, or a cold solder joint or a bad resistor here, or open PCB traces, the signal could get to one side of the resistor and not to the other. If I got in here with the scope and I probed on this side and I saw the audio signal, and I probed on this side and I didn't, that could indicate this resistor is open, It could also indicate there's a cold solder joint on this side or a cracked solder joint, and when I'm putting pressure on it with the oscilloscope probe, it's making contact. So although that's suspicious, I'd have to look at that a little closer. The same thing goes for this resistor. Same thing goes for this resistor. This is a ferrite bead sitting here, this E331. It's a 0 ohm resistor essentially. It's actually a little ferrite bead to reduce noise. Most likely my issue is one of these two electrolytic caps has failed. Don't know that for sure. If the cap has leaked, it's possible that the electrolyte has leaked out and it is etched away, one or both of the traces, and so one of these traces could be open. So if I saw signal here and didn't see signal here, it could be an open trace, it could be a bad cap. The first thing I almost like to do is just replace these two caps. The other thing I want to mention in the discussion here is if you get up to the audio decoupling circle, you'll see 22 microfarad electrolytic caps that are used as really filtering. The thing to notice here is this is plus 12, and it comes down to the plus side of the cap, and the negative side of the cap goes out to this audio ground reference. You'll notice on the cap below that the negative 12 volt comes up to the negative lead, and the positive lead of the cap again goes to this audio ground reference, and that's because this voltage, this minus 12, is lower than the basically 0 volts we'll see here. And so because this lead is more positive in reference to this one, I have minus 12 and 0, the capacitor's in this orientation. So these are polarized capacitors. We get down here and look at this symbol here. The symbol's drawn as a polarized capacitor, but there's this little dash NP off here. And that dash NP says this is really meant to be a non-polarized capacitor. And that's ultimately non-polarized because this signal here can be swinging up towards plus 12 and minus 12 or whatever the voltage it swings. It can swing around the ground reference. And that could put us in a position here where we've essentially got one side of the speaker or the amplifier coming through, and this is, call it 0 volts at that point, and this is swinging negative, and I've now reverse biased this capacitor, and that will over time cause that capacitor to fail. Got the same thing in the left channel here. I ordered a capacitor replacement kit for the A1200, and it looks to me like I got 4 of these 22 microfarad polarized caps, which kind of disappoints me. I want to get non-polarized in here, which was the intent of the circuit designer. There's a couple different ways to do that. Buy a non-polarized cap. You could get two 22 microfarad polarized caps and connect them together in series with, say, the negative leads connected together or the positive connected together. And you could feed the signal through both of those, and the 244s in parallel would give you 22 microfarads. C1 plus C2 divided by the 2 in series. That's possible. So really, there's a signal path here, and to capture a probing list for the signal path, I created this little Excel spreadsheet. And what we've got here is the Paula chip audio outs, in this case for the right channel. We come into that first op amp that's got that audio voltage reference, about 2.5 volts on one side of the op amp, and then the audio in from the Paula on the other side. And that creates what I call a buffered audio out. The audio out here should be swinging above and below the system ground reference. That op amp output then feeds to the input of what I'm calling the buffered audio in. This is the same signal. There's out on this op amp and an input pin on this op amp, and creates the drive audio out. Goes to that DC blocking capacitor and to the final output. So back in the schematic, I've really labeled this audio in, buffered audio out to what I'm calling buffered audio in, to drive audio out to the DC blocking capacitor here, and to the connector. This capacitor exists here to block DC voltages from getting through. AC will pass through a capacitor, so the sound, because it's an AC voltage, will pass through the cap, while the DC voltages generated here are blocked. So it keeps you from taking, the raw voltage coming on the output of this op amp and feeding it all the way through. Only the audio or AC portion makes it through. So from this, I went off and did more research, and I found this page. This is AmigaExplorer.org, or excuse me, AmigaPCB.org. So again, amigapcb.org, and this site amazed me when I found it. So I can go in here and select my Amiga model. I have a Rev 1D4. This is drawn for 1D1, but they should be really close. And I could open this guy up. Let him open here. And what I get is a view of the printed circuit board and silkscreen. But what this gives me is a really nice view into... I've kind of gotten lost in the schematic here. Let's slide over and look at the Pola chip. So the Pola chip is sitting right here. The audio outputs are this pin. As you can see, it's labeled I right, and this pin, which is going to be labeled I left. If we kind of watch the schematic here, you'll see a trace light up in yellow over here when I touch this, which kind of shows me the signal path, if I can get it to do it again here, through, and we eventually get over to where the op amp lives. And if you watch right in the center here, you will see a little bit of yellow light up there, and that's where that signal is getting all the way through to the input of the op amp here. And the same thing's true for the left channel. You'll see a trace light up, although I'm not seeing the corresponding circuit. So we have the left and right audio out, or actually I guess it's the right here and left audio out here, and then we have that audio ground, which is fed from right here. You know, it's labeled A_ground, it's pin 37. And that audio ground makes its way all the way around. If you look at the filter caps here that we looked at in the power supply, and we'll jump back and look at that, you can see that that comes to the positive on one cap and the negative on the other. It's also brought out to the edge connector down there. So if we go back to the schematic, we were just looking at pin 37, comes out of the Pola chip, produces that audio ground, and we saw where that audio ground was connected to the plus side of one of these caps and the negative side of the other. We saw that in the traces. And ends up coming through to the audio ground and the op amps that are connected here, 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 and here. So to me, this was a great resource because it's nice and interactive. I know the whole screen isn't here, but I can remove things like the, I didn't want to remove the silk screen. I can remove the solder mask, makes it a little less cluttered, and I can actually remove the signal line, so I'm just seeing raw PCB and silk screens. It gives lots of really nice views here. We can turn off the power rails. I don't know if this board has inner layers or not. You really wouldn't see it looking through the board. We can turn off the holes. It's just a really nice filter that we can go in here. So for me, spending time looking at the layout of the board, where the chips are, where the major components are, it's just it's really useful because I get an idea where on the board I want to go. We finally get up here to these two DC blocking caps we talked about, where the amplified audio, or the buffered audio I call it, comes in and then comes around to the connectors for the outputs. These two caps live here and here. There's been lots of forum entries talking about these electrolytic caps fail and cause audio issues. If this cap were to fail and leak and it's etched away the trace here or the trace here, that could potentially explain why I'm not getting audio out. The same thing goes for here. There's a little fine trace that comes off down here. I will probably start just by replacing these two caps. They're supposed to be non-polarized. I may actually look in my parts components to see if I can find some non-polarized caps of about the same value that I would just tack solder onto here. The other thing this gives me a really good look at is we have the connector here for the flex cable from the keyboard. And I've seen a few forum entries that talk about how close the solder pad is here to this connector. I don't honestly know if I'm going to be able to get even a fine tip soldering pencil in here to unsolder this without touching this connector. I don't want to melt the plastic in this connector and deform it. That could cause issues with the keyboard not connecting correctly. For my actual keyboard connector on the board, there's the little piece that is the latch. You pull up on it, it releases the cable. You push down, it latches the cable in place. There's a couple of detents on it that keep it from falling off. The detent over here has been broken by somebody, and so that comes off really easy, and that will give me a little bit more room to look down in here. As tight as this is, I may consider removing this connector to do the work. The fear with removing this connector, if you decided to do that, is you need to make sure every pin is fully released from the via on the PCB. If you desoldered all of these and the pin right here was still attached to one of the sides of the via, still had a solder connection, and you pried on that connector, the trace that's lighting up in yellow there, you have a good odds of actually lifting that trace off the board. If I'm to approach this, I would unsolder all the pins. I would go in and wiggle every pin and make sure it's absolutely loose from the sides of the via. The pin is just floating there. And in that state, that connector should just basically fall out. When we get to a later video or actually get on the board, we'll do this. The second reason that this drawing is really valuable to me, can I make that go away, is that, and we'll talk about this in my documentation, having an idea where things are on the board, having an idea where I want to probe. I'm going to want to probe these two pins. I'm going to want to probe this pin. I'm going to probe these two pins to make sure the Paula is outputting audio on both channels and to make sure that this ground reference looks to be 0 volts. I want to look at the various inputs and outputs on the op-amp chip over here. I want to look at the power rails on it. There's where the minus 12 connects. There's where the plus 12 connects. So having an idea where I'm probing helps. This is important to me because the less time I spend with my oscilloscope probe poking around in here with the system powered up, the lower the odds I'm going to have the probe slip. I could have the probe slip from the plus 12 rail here and create a bridge over to this pin here. And if I drop 12 volts on that pin, there's a chance I'm going to damage something. Perhaps the IC itself. So I want to be careful probing around in here. And because these are surface mount components with really tight lead spacing, I need to be careful. The same thing over here with the Paula. Luckily, the audio pins on the Paula are on these two corners here, so it'll make probing these easier. But again, get familiar with the board, get familiar with the layout, know where the major components are. Just so when I'm looking at the actual board, I have an idea. We looked at, kind of in the schematic here, kind of the signal flow from the raw audio through filtering, through amplification to the output. The next thing I created is an Excel spreadsheet, and this will get printed out. And it'll be laying right there next to the board when I've got the oscilloscope probe in there. And this way I can look and say, I want to look at pin U333. I know where that is. Is there a signal here? Yes, there is. I want to go to U15 pin 9. Does that signal appear here? Yes, it does. Signal's getting through to here. I can look at the output of that op-amp and say, am I getting what I call the buffered audio out from it? Is it swinging towards both power supply rails, plus and minus 12? Yes, it is. It may only be plus and minus 1 volt. I don't know. But with audio on it, it should be swinging above and below the ground reference. And then I can look on the second op-amps in and say, yes, that signal's making it to here. And I can look at the out and say, wow, I don't have a signal here. This op-amp is suspicious. But what this gives me is a quick list I can look down to kind of follow along. So I can look at the list and look in the system. And I'm not looking at the PCB and coming back here and finding my next point in the schematic. I have a clear troubleshooting list to look at the major things in the system here that will give me potentially good hints, where the problem may lie. I can also look, U15 is the op-amp. So just a couple of notes here, pin 4 and 11 are the power supply rails. U15 pin 10 and 12 are hooked to that audio visual reference voltage, which I believe should be approximately 2.5 volts. And I see actually a typo in this, so we'll fix this while this here. This is audio ground, which is essentially a filtered system ground. I'm just going to call it audio ground. It's audio ground there. So again, we talked about this audio ground being isolated from the system ground to reduce noise in the audio chain. So again, it gives me a couple places to probe. Paula chip VCC's pin 30 and VSS's pin 8. There's power to the Paula chip. it seems to be working. So again, this will get printed out. I can make notes on it if I need to. So it'll be there on the bench with me. If we come back around to this interactive interface, the next thing I did from this was I did some screen captures on it. Let's go to the end here. So I did a screen capture of where the Paula chip is on the board, and I actually added labels using the signal names that I'm using to make it easy to identify the pins. I can look at the picture printed out and just know I want to touch a probe here, I want to touch the probe here, and I want to very carefully touch the probe here, and just see what I see. Around that op amp, I did the same thing. We've got the op amp here, U15. And we've really got, again, the audio chain as I drew it. The Paula signal comes in on my left. That buffered audio out where I expect it to move to a more AC signal comes out here. That buffered audio out comes down here, the same signal. I've labeled it buffered audio in because it comes in on the left channel here. And I get that drive audio out for the left channel, and that drive audio out finds its way up to the left DC blocking capacitor into the output. So it really gives me, get an easy reference to look, and I'm not going, okay, I need to look at pin 5, 1, 2, 3, 4, 5, and probe. It just gives me a better visual reference. I'm very visual doing this kind of work, so just being able to look at this will guide me through what I need to do. So I'm going to come back around to what I just said and say it again. I do tend to spend time looking at the schematic, understanding the circuit, creating aids to help me with troubleshooting. Again, this will help me spend less time with my hand floating over the board with the oscilloscope probe in my hand or a voltmeter probe in my hand. That reduces the odds of me slipping when I'm not looking and creating a short someplace and taking a chip out. I left in is right here, which is coming from the Paula chip, and I have -12 sitting here. And with these are pretty small parts. With the voltmeter probe, there's the potential I could short these 3 pins together and pass +12 all the way back to the Paula chip, or in the other direction, +12 back to the Paula chip on the right channel. I don't want to do that. I want to reduce the odds of creating additional damage, which is why I do all this work up front. Have I got anything else to say here about this in this first video? I don't think so. I think we talked to the fact that there's various discrete components, resistors, and ferrite beads and things in the audio chain here. I haven't specifically called those out. If, when I go through the high level, I find a spot where the signal stops, I'll come back and identify the components in the chain and probably actually draw in red leads that kind of show the signal flow. And then I'll come back and do some more in-depth probing. I want to give a big shout out here to AmigaPCB.org. Whoever created this, the team or the guy, this is a beautiful resource. Absolutely beautiful resource. The other thing I didn't show you, is we can look at the bottom of the board as well, which again is just really handy. So looking at the bottom of the board, we can see the keyboard connectors right here. We can see the floppy connectors over here. So I have some references on the board. Because this board is mostly surface mount, I don't have like the op amp pins poking through. If we go back to the top of the board, you can see the audio amp's kind of centered down in the center there. That audio op amp is probably sitting someplace about here. Again, this is just a wonderful reference, and the fact that it's interactive is just so beautiful to me. It's just such a great troubleshooting aid. This actually reminds me a bit of the scene in 2001: A Space Odyssey when they've got that module out of the antenna and they're probing around, and on the screen you're seeing, paths light up, change colors, or probing around. That movie was made in the 60s. And in a sci-fi movie, they, envisioned something like similar to this in the movie. Now, what they were showing there was live troubleshooting, and you'd put the probe down, and it would look at the signal and say it's good or bad, but it would kind of highlight on the circuit board where that signal ran. This is just such a wonderful resource, and thank you to the people who produced this. I need to look at Amiga.org or AmigaPCB.org a little closer if there's a way for me to donate some money. I would certainly do that. Just what a beautiful resource. The other shout out here comes back to the person or team that created this document on AmigaWiki.org that's got the schematics in it. Again, I'm assuming this was redrawn. Maybe it wasn't, but it's a very clean resource. I can zoom in very closely here. You know, all the signals are well labeled. It's very well laid out. You know, it's just nice to be, you know, I may print these on my wide carriage printer, and I don't even know what size it prints, 17 by 11.5. These would print very well on it. You know, and it just gives me a great resource. We can see here on this DC blocking capacitor a little closer where the -NP is. That designates that as actually a non-polarized capacitor, even though it's drawn polarized. It's drawn as an electrolytic because it is an electrolytic cap, but it's a non-polarized electrolytic cap. They do exist. So just, you know, something to keep note of. Again, a huge shout out to these guys. This is a wonderful resource. You know, Paula prefers the traditional modes. Just a great resource. Just a great resource. And I don't know if these are cleaned up official prints or redrawn or whatever they are. If they were scanned and cleaned up, somebody put a ton of work into it. They just don't look like they're scans to me. Anyhow, thank you guys for producing this. Again, I'll look if there's a way for me to donate to the effort. I would certainly do so. This is just such a great resource for working on this. The other quick thing to mention, since I forgot to mention, is if I go back to AmigaPCB.org and we get back to the front, is it does cover a number of Amiga models. I mean, really sweet. I do have an A500. You saw me do some troubleshooting on it. I did that troubleshooting really blind. The board wasn't working at all when I got it. Had I known about this resource, I may have actually spent a bit of time on it. Because the 500's through-hole construction, and I'm an old through-hole construction guy, it's a little easier for me to see and follow. The geometries are larger. It's easier to see a trace and follow where it goes. I can spot a via, flip the board over, see the via, and trace the signal on. But again, it's just happened here. We can see that. If I can get it to fire up again, we can see exactly where that pin goes. You know, the Gary chip, what is that, pin 40 there, or 48, feeds up to this via here. We know it passes under the board. It picks up here. It passes on to here. And I'm not seeing where it goes from there, but it's just, again, a really nice resource. And this would have actually been useful to me. You know, when I did the recapping on this and eventually traced down the issues, I think I mentioned in one of those videos that I was looking for a good printed circuit board layout. If you followed my A500 videos, this is actually interesting because this is different from what I did. I may have actually made a mistake in that video now that I see this. Or no, I didn't. I did this correctly. This trace had been lifted off the board and was gone. And it was really hard to see. You know, it seemed obvious where this trace was, but it was really hard to confirm. And it was kind of hard to see how this all went together on the board. And when we get up here to the filter cap, which is sitting up here, it was hard for me to follow and say the plus lead on the filter cap actually came down to here. Now, I'm sure if we looked at the bottom of the board, and sorry for going off on the tangent here, that's probably that link right there. Again, sorry for the tangent here, but you know, this actually applies here. If I'd have had this resource and be able to come in and say, yep, that positive really is meant to connect to here, and it really is meant to come down to pin 2, that would have been really nice. This layout is actually different from the layout of the board I've got. But I would have been able to figure it out. And in that video, you saw me basically use the lead of the bolt filter cap here to replace that lead. So sorry for digressing on this. Even though the board layout is separate from my Amiga 500 board, this would have confirmed the assumptions I was making, which would have been really nice. Anyhow, I've droned on long enough here. I don't think there's anything else to talk about. So I'll wrap this up. In a future video, we will look at my 1200 and go from there.